Hello, AP Calc students, it's Mrs. Marshall, and I am going to be going over some of those derivatives of trig. So section 2.7 takes us into really just doing the derivatives of sine and cosine, as well as the antiderivatives of sine and cosine. We will be doing the other 4 trig functions later on, either next week or the week after. We do need to have a little bit more of some of the derivative rules and knowledge of those before we tackle those couple of trig functions. So just sine and cosine for today, which is pretty straightforward. We have this really nice table here that's created for you guys. Make sure that you are adding those derivative and antiderivative rules to whatever table you are forming. As you notice in the middle, we're going to use the function here of sine and cosine, antiderivative, I know they're labeled, and then the derivative on the right. So we have a connection here with our trig functions. As you can see from the table, the derivatives of sines and cosines actually resort back to the same sine and cosine connections. Excuse me, just the opposite. It should kind of make sense when we think about some of the graphs of sine and cosine and where minimums and maximums occur, so the derivatives would be equal. They coincide with the zeros of the other. So there should be a direct connection. Very sorry. Excuse me. A direct connection with sines and cosines. Okay, so what we want to notice here, though, is that there are definitely some negatives that pop in, and that tends to be the concern of how students remember what is what. So the sine of, or excuse me, the derivative of sine is cosine. The derivative of cosine is negative sine. So you'll need to remember which one gets the negative and which one doesn't. And the same directional idea is that you have inverse, or excuse me, antiderivatives of sine and cosine also have some negative connections there. So you'll need to know that piece. The antiderivative of sine is negative cosine. The antiderivative of cosine is positive sine. So that's really kind of the problem that students have with memorizing. It's just knowing which one's negative, which one isn't. So a lot of different ways that you can try to remember that. I know both Holmquist and I have some different methods, so I'm just going to mention the method that I use to remember which one is which. I will upfront state that I don't necessarily think this is the most appropriate thing to tell students, so I do know that part, but I at least share with students what I have in my head, and then I encourage you to come up with some type of a method to do that. So what I tend to do is think about the negative ideas with using sort of just some acronyms in my head. For example, the antiderivative of sine is negative. And so I tend to think about the antiderivative of sine as the start of a naughty word that's negative that we don't use. AS blank, okay, I won't fill the blank there. Okay, but in my head, I just remind myself that AS blank is a negative word, so the antiderivative of sine is negative. In the same way, okay, I am not a very political person. Okay, I certainly do not want to bring up politics at this time. But in my head, I don't do a lot of things with politics. And so the derivative of cosine, and for me, I think of DC, like Washington, DC, is a negative place because I'm not very political. Again, not necessarily certain that these are appropriate things to be talking about with students, but it's what works for me in my head. So I go antiderivative of sine, naughty word, that's negative. DC, derivative of cosine, is negative. And that's just what I do in my head. So if that might be something that you would use, go ahead. Otherwise, find some other ways. Certainly, home quiz group, you can ask her when you get back and say, what do you use to remember the negatives and the positives? But that's really all you need to be concerned about here as well. We're going to do a few examples in a second. But before we do that part of it, we also want to mention to you guys in this next slide that we have another couple of DE solutions that we want you to be aware of. Very sorry, I can't seem to clear my throat today. The solution to the DE y prime equals k times y is going to be an exponential type of solution. And now that we've seen a little bit of those derivatives of e to the x being equivalent to e to the x, it should make sense here that the derivative of a function, the only way for that to equal back its function is if the function is a base e type of function. So this should not be a shocker to you. And I would say that I would definitely, as students, put this one to memory and remember the fact that the solution to this DE is the exponential piece, because that definitely will pop up. More so than the second fact that we have here in a second, so just be aware of that. We also did several of these types of problems in your exponential work back in the appendix, so you guys should be comfortable with doing a few of those problems, and it works out, especially when you have an initial value that's given to you, recognizing that piece. Hopefully you're feeling a little bit more comfortable. But watch out for that DE y prime equals ky. In this section also, we connect with you guys the fact that a second derivative equaling out to some type of a proportional route, so second derivative of y equals negative k times y. When that DE pops up, the solution to that is this trig expression. And it should make sense. So we were just talking about the fact that derivatives of trig, sines and cosines in particular, lead us to the other version of that sine cosine function. That second derivative would be equivalent for those trig pieces to equal the original function. I would really honestly say that this is probably not something that you should really memorize. I don't think that it's going to come up a lot. If it does come up, and we do have a couple problems in homework, so we're honest there, we would just like you to really be aware of the fact that that's the solution. Find this in your notes and use that to identify the solution piece. Or I have an example coming up in just a few minutes here that kind of also touches base on this particular fact, but at least be able to recognize that the solution to a DE of a second derivative equaling a function belongs to sines and cosines. And if you could do that, that's really probably the best thing there. So put these couple of facts down in your notes and have them handy, but I would for sure go back up and kind of really put this one to memory, kind of like the one that we had where y prime equals 1 over 2y, and we know the solution to that is the square root. I would definitely make sure that those two are in your head. All right, so all we've got left for our lesson today is we're just going to take another few minutes to go over some examples. But this section really is just devoted to you guys working and practicing with derivatives and antiderivatives of sine and cosine. So here, very, very straightforward, was the antiderivative of this f of x function. So let's just practice doing one basic problem, antiderivative, and we're going to use a capital F here notation. And then we're going to take each term, just like we would normally with any other derivative pieces, an antiderivative. Antiderivative of sine, okay, there's that one for me where I remember it's negative. Antiderivative of sine is a negative, and then I have cosine. Antiderivative of cosine is not negative, so I am not switching the sign. So it's opposite negative. And that is really straightforward for that particular example. You can certainly double check by taking the derivative of that and seeing if you get back to things, and just always good practice. The derivative of cosine is negative sine, so that negative negates the negative, returning us back. And derivative of sine is cosine, so that also takes us back to those terms. Those are pretty straightforward. Okay, let's look at one other example here that leads us into using that. And we have worked a lot in chapter 2 here of doing some mins and maxes and inflection and concavity and tying in derivative rules with the t-chart. So here's a question that ties that in along with trig. The picture here shows f of x equaling x plus cosine of x. We see that we kind of have that sinusoidal curve, but sort of at an angle here. And the question is, does f have any local max or min? And we certainly, it appears that we kind of have this increasing function, and it looks like on my graph, I have a couple of spots here that seem like they're constant, and so we're questioning maybe if there's a min or a max in there. Not really sure if that's the case. Are there any inflection points? So is there some type of concavity of parts also that would exchange and have concave up switch to concave down? And if so, where are those? So we kind of have some questions here that we're wondering what is the case. So we're going to go ahead and use our calculus to prove a little bit if those are mins and maxes or not. So of course, for a minimum and maximum to occur, we need a first derivative to equal up to 0. So we're going to find the first derivative of our function, and that is 1. Derivative of cosine is negative sine. So we get this 1 minus the sine of x. And for things to have a minimum or maximum, we would like that to be equaling up to 0. So just a little bit. All right, now to solve that, that means that we're looking for any time that sine of x is equal to 1. And yesterday, Ms. Holmquist went over a video with you guys to understand how to solve for some of those. And specifically, sometimes we have those quadrantal pieces like this. So the sine of x equaling out to 1, we have one choice. We can refer back to sort of the point values that exist in a quadrantal. And we can recognize that the sine is equivalent to a y. So looking for a y equaling up to 1, that would certainly be the point up here, where we're looking at pi over 2, where y is 1. Another option that you have to solve, if you're not always good with using points with quadrantals, I personally instead use more of the graphical approach. So here's the sine curve for 0 to 2 pi. And then I know that 1 equals out to here, which is also pi over 2. So either way that you identify where things are zeros, ones, negative ones, if you're going to use the quadrantals from the unit circle, or if you would prefer to use a sine or cosine graph, either way, we're looking for the solution set. Now, definitely because we know that this is a continuation forever and ever in both directions, technically, the sine equaling out to 1 is going to occur every time we circle about, okay, and go back to either up if you're looking at the coordinate system, or anytime that we're going to be at a positive 1 if we're looking at the graph. So the repeated nature of these things being periodic means that we're going to have a lot of answers. So just to remind ourselves that sometimes there are restrictions, of course, that are given. So look in the directions, and if it says only between 0 and 2 pi, then only answer there, or between negative pi and pi. So pay attention to that part of it. And of course, that would also mean that you have other candidates from mins and maxes. In this case, we weren't told any type of an interval, so we do need to assume that we're going on forever and ever. Right now, our solution in the picture was pi over 2, but knowing that we're going to be repeating over and over again, we're going to add every 2 pi times n. And sometimes we do that as a plus or minus 2 pi n. Sometimes we just have plus 2 pi n. And remember, this part of it is going to refer to the continuation of the repeats. So we're repeating that every 2 pi. So every time we go around the circle over and over and over again, which gives us a lot of pieces. But we're then back to that same question, that we originally asked here. Is this a min or a max? How do we know? So one of the things that we would want to be testing out is plugging it back in may not really answer the question. And so what we want to double check maybe is a quick sign chart. Sorry about that. Okay, and I'm going to just really take a quick moment and think about, that was a little bit too much there. Okay, what happens at pi over 2 in a sign chart? And what happens before that and what happens after that? Certainly this is going to give us a 0 in our derivative. But what are the derivatives before and what are the derivatives after? So if I go right back to my derivative statement here of 1 minus sine of x, and let's just say, for example, I decide to pick some type of a value before pi over 2. Maybe I go with 0. So before pi over 2, if I pick 0, the sine of 0 is 0, and 1 minus 0 is a positive answer. So I've got positive stuff going on here for my derivative. So my function's going up. If I go after pi over 2, and I don't have another 0 until another 2 pi, so maybe I'll test out pi in that section, the sine of pi is also 0, and 1 minus 0 is 1. So this section is also going to be positive. So what this definitely proves to us is that pi over 2 and all of its repeats are not really going to be mins or maxes because they don't change from positive to negative or negative to positive. Instead, they are just going to be stationary points. And that definitely is kind of proof of what we thought happened in our picture because it definitely looked like it was stationary with our just little incremental pieces there. And this kind of gives the proof behind it. So there's calculus involved to do that. So we have stationary points all along the way as no mins or maxes that occur. Now, what about inflection points? What was our kind of second follow-up question to this? And an inflection point is going to occur when the second derivative is equal to 0. So let's just take a quick moment and figure out what the second derivative is. I know you guys have the first derivative there, but I'm going to leave that at the top and just go ahead and write the second derivative down at the bottom here. So the derivative of 1 is 0. The derivative of sine is going to be cosine. So we have a negative cosine as our second derivative, negative cosine. I'm going to scroll down here just a little bit. And so this is our inflection points, and those equaling up to 0. Now the question is, when is cosine equal to 0? If you go with Holmquist's route of looking at cosine being the x's, cosine is going to be 0 at pi over 2, and again at 3 pi over 2. Okay, kind of going back up here to my graphs and thinking about this point here at 0, -1. So both of those locations in the xy coordinate plane have cosines of 0. If you were looking at more of an approach of the graphical piece, I'm just going to make a quick sketch here, sorry, that the cosine graph starts high, it goes down, and then comes back up again in the first 2 pi. And so here are the 2 zeros of the cosine graph, which also confirm pi over 2 and 3 pi over 2 on the graph. So we found both of those. Now that's very interesting because we also now have pi over 2 as not only a stationary point, but it's also an inflection point. Okay, and so if you look back at our graph just a little bit, you'll notice there that when we think about each of these dots, we have sort of this concave down look and then concave up when we talk about sort of this connection to this connection. So that point is not only stationary, but it's also an inflection point. We're going to have another inflection point right around here somewhere where it changes from concave up to concave down. So we kind of have these little chunks, concave up, concave down, as this graph continues over and over and over again. So that seems to definitely be true. The way that we would write this is kind of the final part of our problem. Is certainly we're going to repeat that over and over again. So kind of like the last problem, we would say pi over 2, but then instead of writing every 2 pi n, we're going to write every pi n. So we're just going to repeat that every pi. And if you think about that, 1/2 plus pi is going to be 3.5, and we'll just continue to do that. Sometimes it's written as plus or minus. So that would be a little bit more direct where our inflection points are. It's very, very common for you guys to need to know where mins and maxes and zeros are. As you can see from this example, a lot of times you guys are going to have this type of question to pose to you, or something more like this as well, where sines are equal to 1s, or cosines are 1s or zeros. So we are really encouraging students to kind of get to know these kinds of relationships for those quadrantals, because the mins and maxes and zeros are where calculus is at. So you're going to be doing quite a bit of that piece. This is a good problem. A lot of stuff there. All right, and then one last little part that we have for one example here of a DE. I mentioned to you guys earlier in the lesson that this is the solution to the DE, double derivative equaling up to negative. With this one, we're just showing that that is actually true, that satisfies that piece. And this is probably one that's a little bit more probable that you will see is kind of more demonstrating that part of it. So in order for us to solve the DE, please remember, you guys, that you need to do some plugging in, not crossing the equal sign, make sure that things are equivalent. So obviously we have a y to plug in on the right side of the DE, but we're going to need to have a second derivative of that in order to plug that into the left side. So over here, I'm going to go ahead and find the first derivative as kind of a side note. Derivative of sine is cosine, so we have a times the cosine of x. Derivative of cosine is negative sine, so we're going to go with a negative sine of x, excuse me, negative b sine of x. That's the first derivative. Second derivative, derivative of cosine is negative sine. Derivative of sine is cosine. There's our second derivative. And certainly looking at that, it's pretty clear why in this particular solution does work in the DE, but we're going to follow through very strictly and show and confirm that that is the case. So I'm going to plug in my second derivative from here over into my DE. So I have negative a sine of x minus b cosine of x. And that is supposed to equal negative, and then I stick the y function in there. And we are to show that. And you cannot just leave it here saying that those are equivalent. We certainly know they are, but you need to use some of that, at least one step of algebraic expressions to demonstrate the equality. So you can either factor out the negative on the left side or distribute the negative on the right side, but you should always demonstrate that the bottom of your conformation is absolutely equivalent to the other side. Not just, oh yeah, close enough. Those are equal. It's good enough. And there demonstrates equality. So we have some solutions of DEs, IDPs, just some derivatives, antiderivatives, and certain mins and maxes. All the stuff that we have been talking about in chapter 2 from the beginning, also in this section. So be prepared to see them all. All right, well, you guys can go ahead and get started. Here's your page 147 assignment, and that goes with all of our trig stuff. And remember, you're really just sticking with sines and cosines this time. We'll get to the rest of them at a later point. Thanks, you guys. Have a great day today.